Okay, time to get started. So here's where we were last time. Well, here's where we left off last time. So there's a kind of a cool example here of how to do polar coordinates. This is a classical calculation. The thing is, this is a very narrow application of the idea, and it's not really essential to what we're doing. It's just super cool for kind of historical, cultural reasons. And given that we're behind schedule and everything, I don't think we can quite justify going through it. So you're not responsible for this. It is actually pretty cool, though. If you want to hear a discussion about this, you can go to my older recordings from previous semesters and hear the whole thing. But you don't have to, and suit yourself. Okay, so we're going to move along now and talk about cylindrical coordinate integrals. So it's a lot like polar coordinate integrals. We are doing a change of variables. There is a pullback. There is a pullback domain. There is a stretching factor, all of that stuff, right? But just like with polar, you kind of don't have to draw the pullback domain. Everything you need to know about the pullback domain, you can see in XYZ space. And so the big idea here, for example, let's see here, we're looking at, for example, this theta slice right there. Again, that represents a constant value of theta. What does that look like in XYZ world? Well, again, just like it did previously, it is a kind of a half plane hinged on the z-axis, as I like to call it. So you can see what these slices look like, and it's just a matter of drawing them in XYZ space, looking at the domain you already have, that you already had to draw a picture of. Right? And just inferring what you need from there. So likewise, there are some little tips and tricks. Again, good news, of your 6 options, there are really only 2 that are worth entertaining. Other than, again, highly manufactured weirdo examples that you'll never see in the wild, it's very hard to come up with an example of a situation where one of these is not at least as good as everything else. So I suggest you only consider these 2 orderings of the differentials. And the way you remember these, by the way, is notice that dr and d theta are always together and always in the usual order, just like in polar. So the question is just, do you put dz on the outside or do you put dz on the inside? Okay. Again, don't forget that stretching factor. Oh my gosh, right? Free points, basically. Just write it down, right? Easy money. Get those points on the board as soon as you possibly can so that you don't forget. It's shockingly easy to forget when you've got so much else going on. So my trick, I always write these down all at once, all at the same time, right? And that way, I'm less likely to forget. Okay, so I encourage you to have a similar ritual. And of course, as usual, how do we find bounds? We identify the relevant points. We recognize that they're on certain surfaces. And my pen just died. That's early. We write down the corresponding equations, and then we solve for whatever we need. Okay, so here is a first example. We've got this upper half ball, like so. So, this solid here. And we could do this in rectangular coordinates. You could probably see it coming. We're going to have square roots all over the place if we do this in rectangular, which means we're going to have nasty integrals. This would be a very difficult, almost certainly, right, if we were to do this in rectangular coordinates. So let's not. Okay, so again, let's do this in cylindrical coordinates. Again, that means we're doing a change of variables, right? But we're not going to actually write it down that way. We're not going to deal with the actual pullback. I'm just going to see what I need right here looking at us. So let's, by the way, arbitrarily, I'm going to do my slicing in this order. We'll do it the other way in just a minute. But with that slicing, starting with theta on the outside. This is what a theta slice looks like. The actual slice of which is something like that. And yeah, what's our range of values of theta here? Which values of theta do we get? Slices of this sort. And I hope this is an easy pitch, but it goes all the way around. A geometric appeal. And again, overwhelmingly the best way to do these is with geometric appeals, right? And of course that only makes sense. That's only satisfactorily documented if you have a picture. Make sure to draw a good picture. Okay. So that noted, right? Theta goes from 0 to 2 pi. As per our usual process, we are now going to fix a value of theta, focus only on this theta slice, and now we move on to thinking about the next variable. Let's see, the next variable here is r. Okay. What's the range of values of r? What do I get when I take an r slice of the theta slice? Okay. R slices represent constant values of r. R is the distance from the z-axis. So a constant value of r is just a cylinder, something like this. But again, I'm not actually interested in the whole r slice. I'm only interested in the r slice of my theta slice. So again, another geometric appeal. But how does this orange r slice intersect with this green theta slice? And I hope you'll buy it if I claim that it's just this right here. It's just kind of a vertical line segment. Okay. Which means, by the way, now let's think about first and last. The first one is going to be there, per the picture, where r is obviously 0, right? So our lower bound is 0. And now let's see our last slice. You got to imagine these r slices kind of proceeding along like this. The very last one is going to be this little teeny tiny little slice right there at the edge. Now I need to know what is the value of r there. And notice r, in this case, distance from the z-axis, in that case, also happens to be a radius of that sphere. And the radius is a. So again, a little geometric freebie, right? And you got to love it when that happens. So our upper bound for r is a. Is everybody happy? Alrighty. So, as usual, we now fix both r and theta. In other words, we consider a generic r slice of our generic theta slice. And now we play z games. And so I've got to entertain now the question, okay, what's the range of values of z? All right, well, we start there. Right there looking at us, that's in the xy plane where z is 0. Again, freebie, gotta love it. The last z slice is going to be at that point. What do I know about that point? Well, it's on the sphere, which has this equation. Now, real quick side note, I did sweep something under the rug there. We have a sphere. The very first thing we would typically write down, if you want to write down the equation of a sphere, you typically write it down in rectangular coordinates. I have already converted that into cylindrical coordinates, right? So that is something that does have to be done. Make sure you're good with being able to actually do that. But anyway, there's our equation in the form we need. We're looking for a z bound, so we solve for z, and that then is our upper bound for z. Is everybody happy? Yeah.
Can you, go the other way?
Yeah, oh yeah, I'm going to do that in a second.
No, can you go from inside out?
I find it unnatural. I'm not saying it can't be done. I'm not saying you can't get right answers, but I'm saying I think there's kind of sort of an inherent backwardness to it. I feel like when you do the slicing, you're doing the outside slicing first, because the second slicing is slicing that slice. So if you haven't entertained what these slices are yet, how can you look at slices of those slices? You know what I mean? And again, it's not that it can't be done, it's that I just think it's unnatural. Yeah. Did I see another? No? Okay. All right. Alrighty, let's do this same problem, slicing it with the differentials in the other order. Again, remember the rule, dr and d theta always together. The question is whether dz is on the outside or the inside. Previously we had it on the inside, now we're going to put it on the outside. All right, so here we go. Z slices, constant value of z. And again, geometric appeal, if you have a solid half of a ball like we have, and you take a horizontal cut through it like that, you're going to get a disc. Now again, we've got to play games and think about the first and last. So the first slice is going to be down here where z is obviously 0. So again, get lucky sometimes, score. And then also the last slice, different kind of lucky. There's my last slice. It's right up at the top, right? Where z happens to, again, be a radius, coincidentally, conveniently, right? And being a radius, that means that that is A. Everybody happy with that? Yeah, so this little, what I have in blue here, represents the z-coordinate of that point, which is what I need. It also is a radius of that sphere. So, yeah. All right. So, yeah, all right. So now, as our usual process, we fix a z-slice. Then we go on to the next variable. Next variable is theta. Good news. Theta slices look like that. Pretty clear in this case. Goes all the way around. Right? So 0 to 2 pi. Again, you want to make sure to remember this comes up all the time. When you go all the way around in the theta direction, that just means 0 to 2 pi. Alrighty. And now, as per usual, we fix both theta and z, which means we're looking at this slice of a slice. Now we got to think about the range of values of r as our inside variable. We start here where we're obviously on the z-axis, where r is obviously 0. Again, geometric freebies, gotta love it. And then the last one here, now this is a little bit tricky. That last point there, again, it's on the sphere, which again has this same equation. It's just that this time, you got to be careful about this. This time we are not solving for z like we previously did. This time we are looking for an r bound. So we're going to solve for r. And notice we do then get a different answer. We're talking about the same point that we saw in the previous analysis. Different bound because it's a bound for a different integral. Yes?
Just repeat the thing you were saying about taking a slice of a slice. Like
I don't know what you...
Like for R, or like looking at d theta dz. Like this
oh,
slice that we took, the green one.
Yeah. Well, so this is what we always do when we're looking for the inside bounds, right? We fix the outside variables, and fixing a value of z confines me to this. And further fixing a value of theta is going to confine me just to that little line segment right there.
And then we look for R.
And then we're looking for the range for R. Yeah.
Okay.
Yep.
So here we have two outer variables. Like we would look at theta and z, because they're the.
Yeah, that's all. Whenever you're doing a triple integral, there's always going to be two that are. As you progress toward the inside, at some point you will always have two. Yeah, to the outside. Yeah. Okay. All right. Okay, yeah, so that's the two different ways that you can do this question with the two different differentials. You see kind of how the slicing pattern works. for each of these, and they're not that different from polar. It's just sort of plus a z dimension, really, in some sense. It's really very, very similar. So we're going to move on now to something that's less similar. Spend a little more time on something that's less familiar, and that's spherical coordinates. Now, we're going to start the same way. Yes, it's a change of variables. Yes, there's a pullback. Yes, all the usual stuff that we're going to sweep under the rug because we're going to view it in terms of what we see in the XY plane, XYZ space. What is different is the shapes of these slices and what. Oh, I'm in the eraser mode. I scared myself there. What we have here, these are rho, phi, and theta slices, right? And they're kind of weird looking. And especially, I think, the rho slices, right? Really very weird looking and hard to visualize how these... Can we call it a slice if I can't do that with a knife? You know what I mean? I don't know how to do that. I don't have the kitchen skills for that. So it's just it's geometrically uncomfortable. So here's the really good news. It turns out that all of the seeming geometric and artistic challenge that we would face here is actually all going to just disappear because of the following awesome observation, and that is you're pretty much always going to go in this order. D rho, d phi, d theta. Again, rare, weird, usually manufactured counterexamples. Granted, in the wild, that's not gonna come up. Just always do it this way, and you'll be right. Pretty much always. So that cuts down your options. Now let's think about what that means geometrically. What is the slicing process going to look like, given that I'm going to do them in this order? And well, I'm going to start with theta slices, and theta slices are familiar. It's just like in cylindrical coordinates. Half planes hinged on the z-axis. Super handy. No problem. We already know how to do that. Nice and flat, right? Okay, yeah, but now I'm starting to get scared because here comes the phi slices. And so now I'm going to have to deal with, oh gosh, like a cone, apparently. And how am I going to deal with a cone? And the good news, keep in mind, I don't need to look at the entire cone. All I need to know is how do these phi slices intersect with our theta slices. And the way a cone intersects with this green plane is that there's going to be some little kind of a sort of a ray, if you will, coming out of the origin. So I like to think of phi slices of my theta slice, I emphasize, as being just rays coming out of the origin inside of the theta plane. Again, nice and flat. This wasn't, this is. Is that cool? Yeah. Okay. All right, and then of course the row business is really no problem. The row business comes from the fact that, let's see, oh gosh, I want to erase. Here might, for example, be a phi slice of my theta slice. The row slicing is just keeping track of where do you start and what's the value of row there, and where do you end, and what's the value of row there. So again, all of this curvy, spherical slicing nonsense, no, you're just keeping track of how row is growing from the smallest value to the largest value. So it's actually nice and straight and flat and no problem. Okay. All right, now again, tips and tricks, and these are pretty familiar, I hope. Don't forget your stretching factor. Right? You've heard me say it a million times. A good hack, a little personal ritual for making sure you don't forget it, is to always write down the whole thing there all at once. And by the way, I mean, even if only mathematically, forget about strategy for just a moment, right? This that I have circled here is a thing. This is what dx, dy, dz turns into in the pullback. This is meaningful. D rho, d phi, d theta by itself doesn't have anything to do with the question you were asked, other than that it's part of something relevant to the question you were asked, right? So it just really makes loads of sense to always write this down all together. all at the same time. And again, strategy matters too, of course. Okay, and again, you find the bounds by identifying points and seeing what surfaces, looking at their equations, and then solving for what you want. That's all the same. Let's do an example. Oh, yeah.
Quick question. For the symmetrical coordinates, did you have a preference on which kind of slice you did for those examples?
In this particular example, it kind of worked out equally conveniently both ways. I make no such promises, of course. And depending on the situation, one or the other might be more convenient. Yeah, and I would decide myself by looking at the algebra, possibly the geometry, and asking yourself, would you like to solve for z as a function of r and theta, or would you like to solve for r as a function of z and theta? And one or the other of those, one way or the other, is going to be more convenient, or could be more convenient than the other. And so just let that be your guide. Every example is different. Yeah. All right. Okay, so yeah, here we go. We'll start off by looking at this ball. Not centered at the origin, notice. It's centered on the z-axis. But in such a way that it's kind of tangent to the xy plane at the origin. I like to think of this as a ball that's sitting on the floor, xy plane being a floor, sitting right on top of the origin. Okay, so how would I slice this up in spherical coordinates? Oh, real quick, how would we slice this up in rectangular coordinates? Nightmare. Square roots everywhere, right? Terrible, terrible computationally. Oh my God, terrible. Okay, so let's do our spherical slicing. Remember, with spherical slicing, we're always going to do theta first. Theta on the outside, that is. And theta slices look like this. On this ball in question, they have little cross sections that look like that. Geometric appeal, this goes all the way around. 0 to 2 pi. Just like always. Okay. All right, now the following, you don't have to do this. I find this very convenient. If you don't like it, you don't have to. Suit yourself. I find this to be a little hard to see with. It's a flat plane, but I'm looking at it by some weird angle. In particular, this is what just I think is really confusing. What I have right there, that blue arrow that I've drawn there, in space, that's actually horizontal. On my page, it does not look horizontal. It looks like it's pointing down. It's just, I mean, you can keep track of that, but it's easier to keep track of this kind of stuff the better your picture is. And so now, the possible imperfections in your picture are going to possibly muddy your interpretations of the geometry. It's just a little suboptimal. So my little hack, this is just a choice, and you don't have to do it. I just like to redraw that little plane, half plane that is. Just redraw it like that. Then my disc cross-section, half disc cross-section is like this. And that which is actually horizontal actually looks horizontal. And it's just a little bit easier in terms of geometric intuition. So for your consideration, again, optional. Okay, so let's make phi slices. Now keep in mind, phi emanates out of the origin. All right, so this is what a phi slice sort of looks like, about like that. And we can talk about first and last of these various slices, all kind of like this. Right, and I argue that the first one is like that, where phi is 0, because that's right along the z-axis, where phi is 0. And then the last one, now the last one's a little bit harder to see. The last one, we've got to kind of visualize how these slices keep getting shorter. The closer I get to horizontal, the shorter these little cross sections are. and eventually they're getting really, really short. And where do they finally kind of die out? It's horizontal, and horizontal is pi over 2. That makes sense to everybody? There's another way to say this. If you look at this circular edge to our half disk here, that circular edge is tangent to the horizontal. And so any angle above the horizontal is going to cut into it. Horizontal is kind of in some sense, the last slice, in the sense that anything below that is not going to cut into it. Yeah. All right. Yeah, is everybody on board? Yeah.
Can you just go over the 0?
Well, yeah. So you got to keep in mind that that when I say that we've got phi equals 0 is this. Don't forget where that comes from. That's literally this, and phi is in 3 dimensions. Phi is the angle off of the z-axis. So if you're on the z-axis, the angle is 0. Yeah. Yep. Okay. All right. So now again, fixing a value of phi and theta. So now we have theta and phi both fixed. Now we're going to be looking at values of rho. Where does rho start? Where does rho end? Well, again, you get lucky sometimes. Don't forget that we start there. That's the origin. The origin is where rho is obviously 0. So sometimes you get lucky. And we end here, and this is a little bit of a tricky point. A lot of students will look at that point and think, I don't know where that point is. That's what does that have to do with anything I was given? Don't forget, easy to lose track of this, but where this whole picture came from is it came from over here. It is our theta slice. And so we are actually looking at a point here. This point is actually a point on the sphere. And so, well, how are we going to write down an equation for this? Well, x squared plus y squared plus z squared equals, x squared plus y squared plus z minus a squared is our radius squared. So you write down that rectangular equation. Now we do have to get that into spherical, and this is, again, a good exercise. Everyone should fill in the blanks on this. It's an old chapter 1 thing, right? Section 1.7. We talked about converting from rectangular equations into spherical equations. I claim that this is what you get. Make sure you can do that. You're going to need to be able to do that on test questions, for example. And then, as per usual, we're trying to find a value of rho. So we solve for rho, which is already done. How nice. And there you go. Everybody good? All right. Okay. So a few observations to make. Oh, and by the way, while I'm here, you know what? Just to drive it into the ground. Don't forget your stretching factor, right? So easy to forget. Believe it or not, I have no evidence of this that I can supply, but I did write this all down at the same time, right? And I encourage you to do the same. Okay. All right, so a couple of pieces of advice. You will have noticed by now, I'm sure, that the picture is critical. You gotta have a good picture. Ultimately, that's because we're interested in reasoning, not answers, right? And if you don't give me a picture, then there is no geometric argument. The algebraic argument is intractable, right? Now, non-legitimate mathematical algebraic arguments are easy, but they don't consider all the options, and the argument that what people tend to write down tends to actually not follow. It's not actually a reasonable mathematical argument. It's just, well, I took this algebra for no apparent reason and then did something and got a right answer, right? So algebraic arguments are basically not an option, And so you really need to make a geometric argument, and if you're going to make a geometric argument, you got to have a picture. So I am a big proponent of draw a good picture. A couple of easy mistakes to make. Don't try to make a tiny little postage stamp size picture. Very often you need to refine and look at slices, and then look at slices of those slices, and a lot of stuff gets in there. And if your picture is yay so big, it's going to be a muddled mess, right? So don't be shy about the size. Make it nice and big. Secondly, don't expect that you're going to just see it in your mind. You're going to see what it looks like, and then you're just going to be able to just draw a picture. Nobody can do that. Really, I mean, maybe some people. I can't do that. I don't expect you to be able to do that. I assume you probably can't do that. Expect that you should have to go through several stages of drawing your pictures. Right? Your first picture is going to be bad. Write down a few things as described in the statement of the question, and then you realize that you have a mess. But you can kind of see from your first hack sort of approximately maybe what it's starting to look like. Then your second picture hopefully will be better with the benefit of what you learned from the first picture, and then etc. Right? So cycle through that as many times as you need to. I have in the past gone through as many as 5 different stages, each one being a little better than the previous and eventually having something pretty decent. Don't forget, you do have scratch pages on the exam. Use them, right? Use them as make all sorts of artistic mistakes and artistic screw ups from which you learn and then improve, and then to where you get, okay, I see what this looks like now, and then on the space provided for the question, you can make a decent drawing. Okay. Lastly, I think this is really important. You do not have to rely on, your just natural talent, your current state of, what you know about how to do mathematical drawing. There are techniques. There are little clever observations that can be made that will help you draw better pictures if you understand and digest and implement those ideas. So learn the techniques. I have some recordings on my YouTube channel that I think are good. I don't know, I'm biased, right? But this everything I know about mathematical drawing is in those recordings. So I encourage you to look at those. I'm sure there's others, right? So make sure you know what all the tricks are. And then lastly, let's recognize drawing is a skill. It requires what they call chops, right? You gotta practice and get your hand to cooperate with your brain, right? And that requires doing it over and over and just working out the problems and getting to where you can actually execute proficiently. So anyway, please take all of that seriously. It is a very important skill to have. Next example. It's another ball. Again, offset from the origin, this time offset in the y direction. And that's going to make things different as it turns out. Let's see how those differences play out. Again, starting with, wrong color. Starting with theta, because it's on the outside. By the way, do make a point of, again, always write down your stretching factor when you write down your differentials. Let's get that out of the way. So theta slices, all right. Well, theta slices are half planes hinged on the z-axis. And now begins the geometric appeal, the visualizing the stuff in 3D, right? This ball is just touching the origin. Right? It's tangent to the x-axis at the origin. So all of these half planes that sort of push into the positive y side of the xz plane, they're all going to cut through the ball in some significant way. And likewise, any half planes that are going to the negative y side, swing and a miss. This doesn't hit the domain at all. Everybody see that? Okay. So, with that in mind, our slices go 0 to pi. Sort of just halfway around. Okay. Everybody buy it? Okay. Yep.
So it's halfway around because the sphere is shifted into the positive y?
Yeah, that's right. Exactly. So it just doesn't encircle the z-axis. In some sense, it's only on kind of the right side of the z-axis. Yeah. Okay. All right. Okay, so as usual, we fix a value of theta. We're going to focus on this cross-section. I like to go ahead and redraw this. Again, I just find it a little bit easier to work if I redraw that slice. Now let's think about the next variable. The next variable is phi. Phi slices, kind of like this, again emanating out of the origin. And let's think about first and last. And again, this is just kind of a geometric appeal, but you got to think about how this cross section is a disk. The disk is bounded by a circle, and the circle is tangent to the z-axis at the origin. And again, it's because of the picture. Right? And so being tangent like so, like this. The first slice is going to be straight up, where phi is 0. And then the last slice will be straight down, where phi is pi. Anybody see the geometry on that? Unavoidably geometric, right? I mean, there's just no getting around it. Okay. All right. Yeah.
In the exam, will we have to draw the image from scratch, or like will it be provided and then we have to slice it up? Like.
Yeah. No. I usually don't give figures. Yeah. I mean, it depends. I mean, if I have a particularly complicated one, I mean, I always weigh sort of considerations. If it's hard enough that I think if the question would be too hard otherwise, then I mean, I have done that in the past. But most of the time, I just don't make the examples that hard, and drawing it is part of the solution. So yeah, it's again something you're just going to have to get good at. Yeah.
Technically, we can't solve this algebraically without an image.
I don't see. Well, it is.
Can't solve it.
Well, it depends what you mean by solve. If you mean get an answer that happens to be correct, yeah, sure. But if you mean provide reasoning that actually holds water, I could poke all sorts of holes in a, if you don't have a picture, you claim, just from the algebra I can see this. Yeah, you cannot cite divine intervention, right? Trust me, I see it, right? You can't, that's not mathematical reasoning. You know what I mean? Yeah. So it's just, you really kind of have to have a reasonably representative picture. Yeah. Right. Okay, so proceeding as we always do, now we're going to fix theta and phi. This is our theta and phi slice, for example. And let's think about values of rho. Well, we start at that point. That's actually that point. That's the origin, where rho is 0. Again, sometimes things are easy. Gotta love it when that happens. Let's see here. And then the last value of rho is going to be there. What you got to keep in mind is actually here. Right? Don't forget that what we see on our redrawn theta slice is actually on the actual theta slice on our actual solid. So that point is actually that point, which you'll notice is on the sphere. And yada, 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 changing to spherical coordinates. This is the equation of that sphere. Again, make sure you can do that. I did skip over significant algebra to turn the rectangular equation of the sphere into this. Make sure you can do that. Right? We're assuming that you can do that. That's going to be essential on the exams to be able to actually do that. And solving for rho gives us our upper bound. All good? Okay, so I have one last example. I'm not even going to really do the math on this example. The purpose of this example is to talk about the art. There's a little art trick that I think is very nice. And it is based on the fact that this domain is really awkward and not hard to persuade yourself what this looks like. That's a ball, like so. And then wait a second. Now it's you got to notice this is not a less than or equal. That's a greater than or equal. That means what we have in red here says we're looking for points outside of this ball. And so we're looking for points that are like, outside, like that of the red ball. So inside the green, outside the red. And here's, it's hard to draw this sort of eventual surface because you're going to be tempted to draw like I am here. But there's actually no corner there, right? What we have here, so I like to think of this as, imagine you've got a melon baller, right, and a melon, and you've got a nice round melon ball, and then you take your same melon baller and you take a spherical scoop out of the bottom of that existing melon ball, right? And there's going to be kind of a rim. Like there's an edge, as it were, between these two points that I've got here. And like if you were to poke your finger like here, you're going to first hit melon, and then you poke through the melon, and then you're into that sort of cavity that you've cleared out with your melon baller. And then as you keep poking, then you get back into more melon back there. It's weird. It's hard to draw. And then now we have to face the seemingly very difficult challenge of how do I draw then a slice of this already hard to draw thing. Right, so this is artistically hard and makes it hard to think through the geometry. So here's the trick that I like to pull here, and that is to recognize, well, okay, first a little bit of terminology. This thing that we're looking at, I like to call it an intersection, in the sense that we're looking for points that satisfy two requirements. It's just that one of the requirements is to be in one of the balls. The other requirement is that it not be in the other ball. Right, but I'm going to use the term intersection just to have a convenient term to describe. If you want to take cross sections of this intersection, I make the, I hope, believable case that I can look at the individual cross sections. I can look at for example, a cross section of the top ball, and that's easy. That's just a half a disc. And then I can look at a cross section of the bottom ball, and I can just ask, okay, well, how do those intersect? Well, those individual cross sections were easy to draw. They're half discs. A little bit better picture down here. They're just two half discs, and if you want to know how they intersect, namely what's inside the top one and outside of the bottom one, then you get a much nicer picture here than I think I would have been able to come up with if I had been thinking about the actual shape of the solid and taking actual cross sections of it. I don't think I would have ended up with a picture that easy to understand. Okay, so I think that's a cool little artistic trick. I hope you find that convenient. This is a nice example to go through and think about. Make sure, check the details. Again, make sure you can fill in all the blanks. Notice we get lucky somewhere along the way and are able to capitalize on another little convenient equilateral triangle. It just pops up. Always nice to notice those when they arise. It saves you doing some trig. And make sure you can fill in these blanks. Yeah.
How do you know it's the intersection that above one versus the middle part?
One more time.
Like you see how you colored in the gray, which is
yeah.
the top? How do you know it's that area and not the area between the two?
Yeah. Because up here with the actual solids, we were looking at what was inside this top ball, right? But then outside of the bottom ball.
Yeah.
And so same thing down here. Yeah. Yes.
How did you know that phi is going from 0 to pi?
Yeah, so I'm going to let y'all read through these details. So come to office hours, we can totally talk about that. But I just don't have time to do the full example. But I'll be happy to talk to you in office hours or whatever. Yeah. Okay. Short answer, it's going to have to do with this equilateral triangle right there. Yeah. Okay. Okay. So now, the last thing that we're going to do in section 5.5. By the way, we're still very much not done with 5.5. It's a monster section. I don't know why she wrote it this way, but the following fits in very naturally here. I think this is the time to talk about it. It's a really important integration technique. It's one of my top handful favorite multivariable integration techniques. Because of extensive experience using this method long ago as an undergrad, taking a lot of physics courses, which are not that different from engineering courses, so I predict that this is in your future as well. And yet this topic is extremely undersold in a lot of books. It's barely mentioned at all. And I think that's an outrage. I think this is extremely important and deserves to be discussed at length. So I'm going to segue into this by reminding you of an old theorem that y'all saw long ago. You might have seen it in a different form, but this has to do with odd functions. Y'all remember odd functions from Calc 1? So it's called odd because odd powers of x have this feature that a minus going in results in a minus coming out. One way to say it. And the nice feature is that if you have an integral with an odd integrand and a symmetric domain, now you might have seen this in a Calc 1 class, symmetric domain would be like from negative a to positive a. So this would have been written as integral from negative a to positive a of that f of x. If these two conditions are both given, this integral is 0, and you don't have to find any antiderivatives at all. No integrating. It's a massive time saver when it comes up, okay? Which in single variable calculus is not that much. Okay, now, turns out there is a multivariable version of this. And we're going to start with the two-dimensional version. Oh, I got ahead of myself. Sorry, let me rewind. Why does this work? What is it that makes this work? Y'all have probably seen a picture kind of like this. The high school version of this argument is that this area is canceled by this, negative area, they like to call it, right? Which, okay, is a little sketchy. But that can be dealt with. But anyway, the point is these are the same size, and so if one counts as positive and one counts as negative, then that's 0, and no problem. Here's what I think is a better, a little bit slightly more honest take on this, and that is if I look at two opposite points, p and negative p, and if I look at the term in the Riemann sum corresponding to that one, well, keep in mind color choices. F of negative p is negative f of p. And wait a second, that's related to this term in the summation. And so notice what I have all together then is that the blue and the green terms are negatives of each other. So in the summation, they cancel. Right, so that blue term of the Riemann sum, the green term of the Riemann sum, are exact negatives. Poof, puff of smoke, nothing left. All right. And then there is a version. There's an alternative way to see this. We're not going to talk about this. You don't need to worry about this if you don't want to. But if you are curious, this is an immediate application of a substitution. A real clever substitution argument, and this is what it looks like. And by the way, it's a segue into change of variables, which is why we're doing it in this section. We'll draw the line right here and pick up with the multivariable version next time. See y'all later. Don't forget about attendance.